here. Okay, so seems like we now have many more participants than just a while ago, which is good. Let me just use about 5 minutes to just go through this Moodle page and where the ideas of where you can find the materials. So here probably looks a little bit different to you, but doesn't really matter. You will find the slides and the material. That's basically the important parts. In the material, there's a link to one of the books. There's another book as well. I didn't post a link here, but you can Google it. If you can find these somewhere, I'm not going to require any textbook from your part, but I mean, if you want to, you can look at these, and basically any book that has probabilities and just the basics of statistical inferences, then that'll do. And that's just fine. Most of the material you can find in the slides. These are not completely self-contained, so you will be able to follow these slides and these lectures, do the exercises, then probably you will be able to gather enough, from those slides. You can learn enough, but not completely self-contained. These are more like notes for things that we're going to be going through. But I'm just going to go show you this is the main ideas of how this course works, and it's based on these slides and these contents. So we'll discuss in the first couple of weeks, we just discussed probability, idea of random variables and distributions. We'll talk about what that is. Then we talk about what are called statistics, which means, measures of things pertaining to random things, expected values, variances. Then we talk about certain distributions. I'll explain what the distribution is. Important distributions will be binomial, Poisson distribution, and normal distribution. Basically, that's it. There's also the thing called Bernoulli distribution, but that's the ridiculously simple thing like tossing a coin or flipping a coin or something like this, which I'll explain also. But those are the three main ideas, main distributions. Then we talk about samples and things like sample variance, sampling meaning that we look at something that is assumed to be random and we take a sample, so we measure it multiple times. And then we talk about what are called confidence intervals. And then we talk about statistical testing, which is, the idea of coming up with a hypothesis and then coming up with a test of that hypothesis. And the test of expected values and test of variances. I'm not going to test. So we will test two different things, two different variables, whether they have the same expected value or whether they have the same variance. And yeah, this is very basic stuff in terms of inference. So we're not going to go very deep into statistical inference. In the book that is mentioned in the material page, there's also linear regression and things like this, analysis of variance more in depth. So not going to go there. We're not going to do that all that much. There's some tables here, which, the standard normal distribution table, you can find. I'll explain what these numbers mean. Then there is the chi-squared distribution table, which just, also we'll explain that. And then you can find the students oh, damn. I'll have to reschedule that link because it's apparently that link has been disabled. Well, it doesn't really matter. There's this thing called F distribution, which can be found here. We'll talk about F distribution separately later. So basically these are tables, so you don't have to learn anything, but we will also be using MATLAB. Just very quickly. We'll also be using MATLAB a little bit. Just a second. Just started. So very basic stuff we'll talk about when we do use MATLAB. Very, very basic things. You don't have to know MATLAB pretty much anything about it. Some people ask me whether they need to take a MATLAB course. The answer is no, you don't. So ideas are like, you know, we do basic stuff like we gather a sample like this one, 1.5, 2.1, 4.2. Let's say we have this kind of sample here, and then we just calculate the mean and calculate the variance of X and things like that. So it's all really, really very simple, rudimentary stuff. I'll explain all this stuff, but I hope you have access to MATLAB. All the students should have access to a version of MATLAB online or otherwise. It's not compulsory to use MATLAB, but it'll make your life a lot simpler and a lot easier. All right. And just to, let's go back to the information about the course. Just a very quick recap. We'll do a little bit of a warm up shortly. Did I ever share that MATLAB screen, by the way? Oh, maybe not.
No.
You didn't show the screen.
Sorry, it didn't work. So, okay, like here's an example. So we can have we do stuff which is very basic. So we define a sample here. We can calculate the mean of that, and we can calculate the standard deviation. I'll explain what these mean. We'll do this kind of stuff. Just explain all that stuff later. We'll be using MATLAB for that, and I'll explain it all during the exercises. So that MATLAB usage will be part of only the latter part of the course. So in the beginning, in the first couple of weeks, we don't need it at all. Oh, okay. Sorry about that. All right. So before we get to the actual material, let's have a little bit of a warm up. So because there's so many of you, I'm going to pause. So let's start. So I hope the concept of probability is familiar to you. So most of these lectures or these sessions, the progress will be as follows. I talk for a while. I go through the slides. I talk for a while. We have a little bit of a break where I divide you guys into groups. And within those groups, you then have a short discussion about the topic that we just discussed. And then, you know, we progress for about 2 hours, a little bit less than 2 hours. So when we end before 2 p.m. And then when we're done, you know, we have a short, maybe 5 to 10 minutes of questions. You can ask me questions. You can ask me questions at any time. I'll try and keep the chat window open to see if you have any questions of the material, or you spot any errors somewhere, then I'll just type it in the chat. You can also just put your mic on if you have something to say in between. But other than that, we just have a little Q&A every maybe 20 minutes or so. So let's begin, or before we begin. So here's the thing. I first try to explain to you what the concept of probability means. It's not an easy task to do because mathematically speaking, we can deal with these probability things fairly easily. We can say that something has a probability. I mean, it's just a mathematical concept, and the mathematics we deal with that it's not like it doesn't necessarily have any relation to the real world. The problem is, of course, that, I mean, most mathematics that we teach, this is part of the applied maths program. So it's not easy to justify teaching you math that would have no practical applications. And obviously probability calculus and probabilities and so forth, they have practical relevance. But the question really is that how do we explain the concept of probability? What does it mean? So first of all, I'm not going to make any rigid assumptions as to the nature of probability and you know what randomness means in the real world. So, you know, it's debatable what randomness really means. Is it like lack of knowledge of what we are going to expect? Is it a result of over abstraction, and which we then look at more closely and we see that, oh, this is the thing that we were looking at? Or is it just, you know, is it just truly random in the sense that we do everything exactly the same way and still the result is different? And you know, any and all of these ideas have their places, but we don't really care. I'm going to teach you the mathematics of it, and then you interpret it the way you want to. So we'll look at some of the situations where we use probability calculus and probabilities as models. And then in those situations, you know, you have to either believe it or not believe it. Most people will believe it. And if you don't believe it, then, you know, well, you're my students, so I can't really suggest this. But if you weren't my students and you didn't believe it, then I would have this really nice game that I'd like to play with you. I mean, there's just a little bit of wager there. You see what I'm saying? I mean, just, you know, if you don't believe that probabilities describe the real world, then by all means go and play on an internet casino or something like this. But, you know, those are based on the idea that we control for probabilities, laws of large numbers. Some people sometimes win, but, you know, the house always wins, eventually at least. All right. Well, this brings to us to the topic of what was the original application of probability calculus. Was really gambling. I mean, that's why it was devised. And it were games of chance, as they are called in English often. And these games of chance had, you know, unpredictable outcomes, and people would place a wager as to, you know, what to expect. And then, you know, someone would win and someone would lose. And the idea of probabilities came really from trying to figure out a way to run the game for a long time so that you eventually win. You may lose sometimes, but on average, or when you play for a long time, you win. If you are the game maker. I mean, of course, if you misapply the theory, then you can be a game maker and lose money. But those guys go out of business. But there are various real life phenomena also. And we'll talk about the latter part of the course, and we'll just devise a mathematical apparatus here and mathematical way of thinking about probabilities. And then we go and apply it to real world phenomena. In that part, we talk about statistics or statistical deduction or analysis, or, you know, trying to figure out some phenomenon from measurements that are somehow random. When you have many of those measurements, we call those statistics, really. So we must talk about the concept of, or the question of operationalization. So it's a really hard to pronounce word that really means that way of making your mathematical theory operationally relevant. And by that, we mean basically what real life phenomenon or real life thing does some number or some result that we get from our theory, what does it correspond to? So we will talk about that a little bit. So here's one puzzle that I want you guys to think about. So we have this following game. You take part in a contest. The contest itself is irrelevant. You are given a prize, and you are given a choice. The guy who's hosting the game gives you a choice. There are two envelopes, A and B, and they tell you one thing about these envelopes. They say that we've picked up some random number of some random amount of money, some number of euros, let's say X euros, and then we place that amount of money in that envelope, and the other envelope contains twice that much. And it has been arranged in such a way that, for instance, they use bigger bills or something in the other one, so that, you know, they look outwardly, they look exactly the same. You cannot tell out from outside which contains more money. You can select whichever envelope you want. You can look at it, and if you think there's not enough money there, you can change the envelope. This is you can do this, right? This is a game, right? I give you two envelopes. You can choose whichever you want. You open it, and if you're not happy with the amount of money there, you can change. And now, of course, there's a 50-50 chance that you pick the one with the more money, and there's a 50-50 chance that you picked up the one with the less money, right? So if you see some number of bills or some amount of money in your envelope, let's say 100 euros, the other envelope will contain either 50 euros or 200. You don't know which, but there's a 50-50 chance that you pick the smaller one. So, you know, 50% chance that there's 200 there, and 50% chance that there's 50 there. Both of them are equally likely, right? You picked it at random. So if you keep the current envelope, you get X, let's say 100. But if you change, what is the expected value? We'll learn about this. There's nothing fishy here. The expected value, you just, you know, there's a 50% chance that you get 2X, and there's a 50% chance that you get X divided by 2. So that's about 1.25, so 1 1/4 X payoff if you change. So on average, if you change the envelope, you gain. It pays to change the envelope. But, you know, let's say now that the envelopes were red and blue. You pick the blue envelope, and now, you know, changing to the red one, it has a payoff of 1.25x. But the same holds true if you pick the other one. So it looks like you always want to open one envelope and then pick the other one, no matter how much money you see there. But this can obviously be true because, you know, if you predetermine to do this, then, you know, it's a 50-50 chance you get more or less, but you won't get 1.25 on average of what you got. So this is a seemingly impossible situation. So when I'm not going to tell you anything about how to figure this out or how to understand this. I'm telling you this in the hopes that you will, during this course, when we learn things about probabilities, that you will learn to understand what is going on here and why this is a problem, why this analysis is problematic. Right? So this just if you don't understand the puzzle right now, don't worry. We'll return to it. I just urge you to return to this puzzle every now and then. Whenever you see something that says, "Oh, I think I'm kind of going to understand this." It'll come later during this course, but, you know, if you feel like you understand it now, you can discuss it shortly. We'll have another 10 minutes of me talking, and then we'll have a little break. But this is just a puzzle to ponder. I just wanted to give you the seed of thinking. Right? All right, let's move on. So we'll talk about the concept of probability. And the important basic concepts of probability are based on the following concepts. And I hope that you will do the task of trying to understand what they mean. There's the concept of random experiment. I'll explain it in more detail, but it's something you do where you get an outcome. Think, let's roll the dice. we get some number, our experiment is rolling the dice and the result is something. I mean, that's the experiment. We get, let's say we roll one die, we get a number between 1 and 6. That's random. We don't know which we're going to get, and you know, whatever. Random variable, we can call this random variable is called the thing that you measure, or the thing that you get, the value that you get when you actually conduct the random experiment. The random variable is not the value you get, it's basically the placeholder for the value that you might get. So let's say I have a random variable x. My random experiment is throwing the dice. So x is the value that you get from the dice. But x is not a particular value. It's one of the values between 1 and 6. And every time you carry the random experiment, the random variable gets a new value. Then there's this thing called sample point. That's an important concept as well. Sample point is a point it's one of those results that you may get. It's an actual point. So in this dice case, there are 6 different sample points, numbers from 1 to 6 in your die. And sample point is the outcome of the random experiment. Sample space is really, it's the set of all possible outcomes. In this case, the die has a sample space of numbers between 1 and 6, integers 1 and 6. It could also contain 0 and 7. You know, this is not impossible. It's just that 0 and 7, they have probability 0. They don't happen. And an event is an occurrence of the random variable that is not tied to a particular sample. Sample point. It's tied to a set of possible outcomes. Let me give an example. The roll of the dice is an odd number. The roll of the die is an even number. Those are 2 possible events. So the roll of the die is an even number if we roll it and we get 2, 4, or 6. So the event is some set of possible outcomes. All right. So these are the basic concepts around which we will build this theory. The goal of this probability calculus that we develop here is just that we develop some mathematical tools to describe randomness. And by randomness, we mean informally anything or a phenomenon, anything that we can measure or somehow observe that may have different results different times we observe it. So for instance, the weather outside may be a random phenomenon. Sorry, I have not put the, I'm gesturing here like a madman, but not showing it to you. So the weather outside may be a random phenomenon. So let's say that I put on the thermometer, I put it outside, I get some number in it. That's a random variable in the sense that during different times, I get different number. It's not random necessarily, physically random. You know, maybe we know that it's determined completely by something like, you know, the sun, how much does the sun shine, what is the cloud cover, and so forth. But it is random for all intents and purposes when I measure it from the outside and I have no other model of what is happening. And the random experiment, I mean, the phenomenon itself is whatever, the weather, meteorology. This is not a course on meteorology, so, you know, it's not, we're not going to discuss weather. We have a very complicated model of the weather. But our model of randomness may be just, you know, we take some measurements during the year of the temperature, and we get some distribution or some idea of how probable what kind of temperatures are. And we generate a random model of randomness. The idea of the random experiment is that we don't know what it is beforehand, and the model itself does not predict the result per se. It can say that certain results are more likely than others, but it will not predict what the result is. At the far end of the spectrum, we can think the roll of the die. I mean, it doesn't tell you anything, you know, what is it 1, 2, 3, 4, 5, or 6? The model only tells you that in this case, in an unloaded die example, it just tells you that all the 6 numbers are equally likely to happen. What does this mean? Well, I'll explain it shortly. The model does predict the behavior of several experiments in the sense that when we do a large number of experiments, some kind of regularity or pattern emerges. This is what we call distribution. So if we roll the die, 1,000,000 times, we'll get roughly 1/6 of those results will be 1, 1/6 of those results will be 2, and so forth. It's not going to be exactly like that, but the model predicts that the more experiments we make, the more closely it should resemble this result that they are, pretty evenly distributed. It's a distribution there. So the result is understood as a random variable, and instead of a particular value in this case, it's whatever the experiment reveals. It reveals different things different times. So whenever we look at this variable again, we get a different result. So like I said, the sample point is one of the possible outcomes. So in the case of weather, depending on, let's say, how accurate our thermometer is. Let's say our thermometer is a digital thermometer, and it gives the result with the accuracy of 0.5 degrees. Let's say it's from -35 to 65 degrees centigrade, and with 0.5 degree intervals. So our sample points are all the numbers there between, and the halves, from -39 to +60, and then all the halves, like 1.5, the next one is 2, and so forth. The sample space in this case is the set of possible results. Or let's say we are using an old mercury thermometer. Mercury has a freezing point around if I'm not mistaken, it's around -30 or something, and it's a boiling point somewhere. It's pretty high. It's a pretty high boiling point. I don't remember exactly, but I guess it's over 200. I don't remember. Let's say it's 200 centigrade. I don't remember exactly how it is, but if you had a mercury thermometer, then that would be the range of values that you could get. If it's higher, then it explodes. Then maybe you have the result is frozen, some number, or thermometer blown up. So you have two results of the random variable which are not numbers at all. Frozen thermometer and blown up thermometer. And an event is some subset. In the case, like I mentioned, the case in point was for the roll of the die, even number, odd number. In the case of thermometer, we may have an event like, let's say that we're going to go skiing, cross-country skiing. We have to lubricate our skis based on the weather. So you may have 3 different events. It's over -1, which means that we have to put this, around 0 centigrade lubrication. Then it's between -1 and -10, and then it's below -10, let's say. So we have 3 different events, and we have 3 different these waxes that we put on the skis based on what the thermometer says. So we have 3 possible outcomes of the event. The number can be something else, but the number range is the event here. All right, let's pause for a little while. That's enough talking. Let's just march on, and we'll have another small session shortly in about 30 minutes or so. Okay, so let's carry on. So here's an example of a situation which, I hope you are familiar. Not everyone, the people from around the world, so not everyone is familiar with this usual deck of cards with 52 cards. Like there's diamonds and hearts, and then there's hearts, diamonds, clubs, and spades. And there's the red ones and the black ones. The hearts and the diamonds are red, and the clubs and the spades are black. Right? So they have these two different colors in these cards. And then each suit has numbers from 1 to 13, or if you consider the ace is often considered a 14 in certain games. So, and in blackjack, it can be either 1 or 11 and so forth. And they can be numbered from 1 to 13 or 2 to 14, depending on in poker, it's usually considered 14. So the ace is 14 and so forth. So if we consider these cards as either the event that the card is black, so the suit is either clubs or spades. And if we consider also the number, then there's 52 different outcomes, and 26 of them are black, and 26 of them are red. All right, and depending on what aspect of the card you are focusing on, then your sample space may contain just 4 points, it may contain 52 points, or it may contain any number of points depending on how you abstract. So usually we think of it as having 52 different outcomes because it's a number and a suit. Consider the idea of rolling dice. We have 2 6-sided die, and let's say that they have, again, colors, like let's say there's a green and a red one, or if you're colorblind, that's bad. Let's say there's a blue and a yellow, or even that's a problem. Well, let's say there's a blue and a red one. That's usually not a problem for anyone, seeing those two different colors. So there's a blue and red one, and we say the first one is the blue and the red one is the second one. So we get a 2 numbers, and blue and red is 1 1 1 2 1 3 and so forth, and all the combinations. So there are 36 different possible outcomes, and our sample space contains 36 different situations, depending on which of the die is which number. Let's say that we have an event which says that the sum of the dice is equal to 4. So we have 3 different outcomes: 1 and 3, 2 and 2, 3 and 1. Here's an example. Another example: we flip a coin. And the random experiment is we see how many times we flip until we get heads. So if we get tails, we flip again and flip again. We flip until we get a heads. So the random experiment is the throwing of this coin until we get a heads. And the result is how many tosses did we make? We make at least 1. If it's a heads, we stop. If we get tails, we toss again, and if that second one is a heads, we stop. So if we mark them with H and T, then the result sample space is infinite. It can be heads, it can be tails, heads, it can be tails, tails, heads, tails, 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 heads, and so forth. All the possible outcomes are possible, but of course they're very, very unlikely. They get less and less probable the more there are these coin tosses needed. But still, the sample space itself is infinite. So this is something you should understand. The sample space can be infinite. All right? So the sample space is either finite or infinite. We can organize these as a list, even if they're infinite, in the sense that we can number them: 1, 2, 3, 4. How many tosses did we make? So the heads, tails thing, there can be any number of tosses, infinite number, but we can just number them all. So we can consider them to be given as a list. And if we can do this, if we can list, even in an infinite list, if we can list this sample space, then we say that the associated random variable is said to be discrete. It's discrete because we can associate a number to each of the possible different results. That's an example of a discrete variable. So the discrete random variable, the role of the die is obvious. It's a finite number. If it's a finite number, then no fine. If it's infinite and we can list them or number them, then we also say it's a discrete number. So we say that it's a countable set. So when the sample space then, on the other hand, consists of an interval of real numbers, we say that this random variable is continuous. So let me give an example of a continuous variable. Let's say time. I put on this machine, let's say I press this button, and by some random means, it's going to take some time between 0 and 20 seconds before it rings a bell. The moment the bell starts ringing, the timer stops, and that's the random variable. So this is a continuous thing. I mean, obviously there may be instruments that measure the time that have a fixed and a limited accuracy. But if we consider the actual time to be continuous, then we could say that it's continuous. It's debatable. That's a philosophical question whether such variables can actually exist, but really, honestly. Another example, let's say we measure how tall people are. And again, that's really, there are inaccuracies in measuring how tall people are, but let's say that we have some really accurate way of measuring how tall people are. That's a continuous, I mean, someone can be a very small fraction of a millimeter taller than another one, and we can still detect it. Again, not necessarily, this accuracy issue comes to play here, but we can abstract and think that it's a real number, and we can, the height of a person is a real number, and we can think of it as a continuous variable. Here's another example. We measure the time we put on a machine and it breaks at some point. No machine lasts forever. We measure how many times, how many seconds or minutes or years or whatever the time is, a reasonable time interval. We measure it, and when it breaks down, we record the time that it took. We can think of that as continuous variable. Let's go through some of the set theoretical things. I mean, and these are just Venn diagrams, but I hope that you know enough set theory, or you understand how sets work. Because here's the thing, we call this omega. Let's say this omega is our sample space, and our sample space has some possible outcomes. And let's say we've circled this and call it A. This white circle here, points inside that white circle, they're called A. And the complement of A is all the points in our sample space that are not in A. So the complement of an event is defined as the event didn't occur. So let's give an example from here. Let's say that we measure the time for the machine to break, and let's say that it's measured in weeks. And we have the event that the machine breaks down in the first week of March, okay, or the second week of April, let's say. Then that could be A. The set of possible events is, let's say that the machine is never going to be operational for more than a year, and it breaks at some point. So the other points here would be it broke down some other day or was decommissioned at the end of the year. The union of events, union of two events. Let's say you roll a dice. There are two possible events. The number, let's say that we have 6-sided die. So we have numbers between 1 and 6. There are two different events. We say that one event is, the number is odd. So it's 1, 3, and 5, let's say. And then let's say that there is another event that the number is big. The number is big means it's 4, 5, or 6. Now the union of big and odd is, either it's big or it's odd. Well, 1, 3, 5, those are the odd numbers, and then 4, 5, and 6 are the even, the big numbers. So if A is odd and B is big, then A union B contains 1, 3, 4, 5, 6. Intersection, both A and B. So big and odd means 5, because that's the only number that is both big and odd. The difference, big and not odd, would be 4 and 6, right? A happens, but B doesn't. So this is just basic set theory, and I'm using set theoretical notations here because really I associate the events with sets, and I hope you will be able to do this too. So we will. Then there's this concept: two events, are they disjoint or not? Okay, let's give an example that the number is big. Let's say that's A. And then let's say the number is 1. Let's say that's B, okay? It cannot be big and 1 at the same time. So these two events are disjoint. Let's say, you have you pick 2 cards off the deck. Sorry, you pick 1 card from the deck. And there are 2 events that we associate. We ask, is it black and is it hearts? Well, if it's black, it cannot be hearts because, the hearts are all red. So black and hearts, those are disjoint events. So this is important to understand, that the concept of disjoint. Disjoint means that the 2 things cannot happen together. They cannot happen at the same time. We have 2 possible results. So, it cannot be both hot and cold. Let's say we define a hot weather outside. It's anything over plus 25 centigrade. Those of you who are from really, actually from countries where the weather is habitable to human beings will laugh. 25 is not hot, but in Finland it's hot. And then we say that it's cold if it's less than minus 10. And then hot and cold are obviously disjoint. It cannot be both hot and cold. But, if we have multivariate, multidimensional weather, like, it's raining and it's hot, that can happen. Not in Finland, but, in places, I've lived in Singapore, then it can still rain while it's really hot. I know Finns won't believe me, but, those of you who are actually from hospitable climates know that it can be hot while it's raining. Okay. Here's another example. Consider a deck of cards, we draw 1. The sample space consists of all these 52 different cards. The event is card is red. Event B is card is hearts. C is card is ace. And D, the card is spades. Oh, sorry, there's a typo there. Let me fix that. Red, no, the red. I mean, card is black, not red. Okay, I'll divide you guys into groups again. I'll have you guys come up with these. Card is black, obviously, it's not red, so it's the complement of A bar. Just, I can annotate it here. So that would be, my handwriting is really bad, but it's A bar. Ace of diamonds, card is an ace and it's a diamonds. Well, how do you come up with diamonds? So that's not easy. The diamonds.
Sorry, I can't see what you're writing.
You cannot see?
Yes, we can't.
Oh.
Yep.
I wonder why this is, the A here that I wrote is not visible.
Nothing.
Because you're sharing just one window. You should share the entire screen.
Yeah, that's probably so. Yeah, okay. I'll do it. Share the whole thing. If I share the whole desktop, like so. Now, let me try it again. So Not red, so that's A. Can you see it now?
Yes. Now.
A bar.
Yes.
Yeah. Sorry about my handwriting, you know, I don't have the drawing board just yet. So ace of diamonds. So, well, first we have to decide what is diamonds. I mean, it's not hearts, but it's red, right? So the card is obviously red. And it's an ace, right? But this is just a red ace, so we have to figure out that it's not hearts. So we can do it like this, but it's not hearts, right? It's a red ace, but it's not hearts. All right, that's one possible way. There are multiple ways in which you can express this. It's a black ace. Well, it's not red, and it's an ace, so it's an ace, and it's not red. Alternatively, it's one of those aces, but it's not red. That's also possible. All of these are possible. Card is a club. Well, it's not red, and it's not spades. So again, it's not red, and it's not spades. So we can take D here. Da, da, da. All right. That's one possible. There's not one correct answer. It could be many different ways in expressing this. All right. This was just a very quick rehearsal of using the set theoretical notation here. Let's carry on. So, what do we mean by probability? We want to associate the probability to events. We don't start with sample points. We could do this for sample points in the discrete case, but obviously if we have a continuous variable or infinite sample space, it's a little bit tricky to define the concept of probability for an individual point. Well, for discrete infinite sets, it's fine, but for continuous variables, it's hard to define what probability might be. So let's come up with some concept of probability. What does a probability of an event mean? And here we discuss the issue, you know, this requires us some connection, requires us to build a connection with the real world and mathematics. That's always tricky. It's really always a little bit tedious and tenuous at best. I mean, there is always some kind of a open to debate there whenever we do this. But let's do it now, and it should be relatively fine. So, assuming that we've reached a consensus as to when an event is said to happen. So let's say that we have a consensus of we measure people and we say a person is tall if he or she, well, if it's a male person, the average height is something just in Finland, it's just around just under 180 centimeters. So let's say that a person is tall if they're over 187. Let's say a male person is tall if they're over 187, and let's say a female person is tall if they're over 178, which roughly the height difference is about 9 centimeters for men and women, roughly. I think it's a little bit over that, but never mind that. Let's say that we have this number. We've come up with numbers to say when a person is tall. Now, we want to say, what is the probability that a random person that we encounter is tall? Okay. So what we do is we go to let's say we go downtown, we go to the street and we measure people. Well, let's say we have a laser there that measures how tall people are, so we don't have to really interview them. We just see them passing by and we measure how many they are. We measure the person, and if they're tall, we increment some number. We do this n times. We count how many tall people we see. We do n experiments. Let's say we do 1,000 experiments, and let's say that we see 100 tall people. So we come to the definition that 10% of people are tall. So the probability of encountering a tall person is about 1 in 10. I have no idea whether this is true. I don't take my word. This is just a made up example. Or let's say that we throw the dice again, and we say that the number is even. What is the probability? We roll the die 1,000,000 times, or not 1,000,000 times, but let's say 1,000 times, or 1,000,000 times, doesn't matter. We count how many times we get an even number. We divide that number by the number of rolls. We get the relative frequency of even numbers. So we call this Pn. It's not really the probability, but it's some kind of estimate or some kind of idea. You know, this is about the estimate. And we can define the actual mathematical probability as the limit of this Pn as n goes to infinity. So if we were able to measure every single person, I mean, this n goes to infinity would, if in case of tall people, would mean that every single person, but in the case of the rolling the dice, really, it would have to mean actual going to infinite rolls. And if we can somehow infer that this approaches certain number, then we call this number the probability. In the case of persons, people, then, you know, the tallness of people, you know, that would be the proportion of tall people in the whole world. Whereas in the case of rolling the die, it would be the number that it approaches when we roll the dice. You know, how many times did we get an even number? It should be 50-50, but, you know, who knows? Maybe the die is loaded. Maybe it's there's a weight somewhere that makes it more likely to be number one, and then because of that, the even numbers don't occur quite as often. It's possible. So this probability is defined as the limit of, if we were to conduct the experiment infinitely many times, then how many times did the event occur out of n? So the number of times it occurred divided by the number of times you conducted the experiment. The relative frequency. This is a little bit unsatisfactory because we cannot carry out in any reasonable time, we cannot carry out infinite number of experiments. So it's purely theoretical. There is an observation in the real world that if we have modeled a phenomenon as random and nothing changes in the way we carry out the experiment, and the experiment is really carried out exactly the same way, then as n gets very large, different people tend to get the same very close to the same relative frequency. So if I have a manufacturer who manufactures very good, well-made dice, and I pick one and I give each person in this classroom, I give each one of you a 1 dice, and I ask you to go home and roll the die, I don't know, 1,000 times and count how many times you get an even number. Then everyone gets roughly around 500. Someone may get 430, someone may get 570, but I'm pretty sure that everyone, well, not that many, you know, no. Someone may get 450 and someone may get 550, but everyone else is going to be between those. I could bet some money on that. And the differences are relatively small. And if we calculate all of them together, there's 45 of you. So if 45 people roll the die each 1,000 times, that's 45,000 die rolls. And then I'm going to guess that the number of even numbers that you get is very close to 22,500. It may be off by a few, you know, maybe 22,600, maybe 22,700, no, 22,600 or 22,400, but definitely, you know, not much more further from that if they're well-made dice. So they tend to be the same. So we can rely on not exactly on the estimate of probability, but if n is large, then we get roughly the same relative frequencies when we do it in different situations. The problem, of course, is that finding a large enough n to get a reasonable estimate empirically of a probability depends heavily on application. So what mostly what we do is we make some assumptions about the phenomenon, and we carry out a few experiments, and we assume that our relatively small n actually gives us a good good estimate. We'll get to that shortly, but you know, just a word of warning: there's no hard evidence or no mathematical proof that that works. It's simply an assumption. So this idea of carrying a large number of experiments and then coming up with an estimation of what the probabilities are, or interpreting the probability, theoretical probability, as, if I were to conduct this experiment very many times, I would get something that is very close to this. And the more experiments I did, the closer it would be. This is called the frequentist interpretation of probability. It simply states that if we were to carry out an experiment many, many times over, then the numbers would look like, the relative frequencies of the numbers that we get, or the relative frequencies of the events that we get, would look like the probabilities that the probability theory, theoretical model predicts. This is the kind of interpretation that may look satisfying, but it's not really satisfying. It's not very good, because the actual probability occurs only at infinity, and there's no way to express anything like the rate of convergence. How fast, how big an n you need. Nothing in the theory states that how big an n you need, so to get a reasonable estimate. So, unless you do that, then you don't have a sound, satisfying mathematical theory. You can say that, okay, if I did it infinitely many times, I'll get closer and I'll get a good estimate. But, you can't do it infinitely many times. There's always a finite number of times that you can do it. All right? But it's good enough for our purposes at this time. We'll discuss a little bit of other ways of thinking about probabilities. The so-called classical probability applies, you can dispense with the frequentist approach. You can think of a classical probability. This comes from the games of chance thing, where the sample space is finite, and we have no reason to assume that the sample points are different in any way, or alternatively, we have some strong reasons to assume that every sample point is equally probable. This is what I like to call picking up balls from marbles from a plastic, not a plastic bag, from a bag. You have a bag that is opaque, you can't see through it. There are marbles in it. You put your hand in it, there are different color marbles in it. You put your hand in it and you get out a marble and it has certain color. So there's no reason to assume any of the marbles that you pick it at any more higher probability than another marble. And let's say there are 10 red marbles and 10 blue marbles, and you pick one out, then the probability is 1/2 that you get a red one, right? So this is the classical probability. So this can be applied, the idea of classical probability can be applied in games of chance, like rolling the dice, picking up some objects from a bag that you can't see and they're well shuffled, picking up a card from a deck that has been shuffled properly, and so forth. So usually in these cases, we assume that a single occurrence. Sorry? Did you have a question there? Okay. I didn't quite hear, but maybe that was an accident. Okay, so you pick up a card and it's any one of the 52 cards. Each individual sample point has the probability of 1 over n, where n is the number of sample points in your space. In the case of the deck of cards, there's 52 different cards, so each card is equally likely to be on top. In most real-life technical applications, sample points are not actually equally probable, and this definition cannot be used. So be forewarned. This applies to the very, very simplistic, I would say, simplistic cases of picking up balls from a bag or picking up the top card or rolling the die. But it doesn't really work in situations like you know, let's say that for one reason or another, we assume that there are as many men as there are women in the world. It's roughly 50-50. It's not quite equal to that, but let's assume for now. Let's say that that assumption is safe. Let's say that's not a problematic assumption here. And we pick a person at the university. And we say that, okay, that person has a 50-50 chance of being a male or female. I'm sorry that I'm discounting all the other possibilities here now, but let's just assume that there is no other. Let's just make this assumption now. This is a probability exercise, not. So, but that's a ridiculous assumption, because if we pick the person at the Hervanta campus, then there are more male students at the Hervanta campus. If we pick a student at the center campus, there is a little bit more female students at the center campus. So if we pick from one campus, then we don't get a 50-50 probability. So I'm just saying that the classical probability assumption of equally probable it breaks down very rapidly in the any real life application. It doesn't really work unless you have a very strict and very narrow situation where you're using this model. And be that as it may, usually when we derive things from with these classical probabilities, we do complicated combinatorial problems. We don't go to combinatorics that much in this course. We'll just discuss some of the simpler ones. It's a very simple case. Assume that the random experiment consists of p different stages where each has ni possible, each stage I has ni possible outcomes regardless of the outcomes of the other stages. The sample space size is simply the product of the sample spaces in these different situations. Let me give an example. Think, you roll one die, you pick one card, and then you, let's say you, well, okay, let's have two. You roll one die and pick one card. The die roll is 1 in 6, so it has a sample space of 6 possible points. The card has 52 possible outcomes. Then there are now 6 times 52 possible outcomes of this experiment where we roll the die and pick a card. If we roll 10 different kinds of dice, then the first one is 6-sided, and then there's an 8-sided, and there's a 10-sided, and so forth. Then, the number of possible outcomes is the product of all these, assuming that we consider the different occurrence where we get a different number from each, not the sum of all these, mind you, that could be radically different, but just, as green die, this, red die, this, blue die, that, yellow die, that. It's a total of 4 different numbers, and the combinations are just multiplied together. This is fairly simple. It comes from the simple Cartesian product of the sets, right? Because the Cartesian product of of the first set, and the second set contains the number of these times the number of these occurrences. So if you roll 2 dice, the red one and the green one, and they're all 6-sided, then you get 36 different possibilities. If you add the numbers together, then that's a whole different game. But let's say that we have these 2 different situations. This is known as the product rule. Here's an example. Let's say a person has 3 different hats, 5 different coats, 2 sets of pants, and 3 pairs of shoes. They can all be worn together. And the person needs to get dressed. Say they have 90 different ways of getting dressed. Pick one of the 3 hats, pick one of the 5 coats, one of the 2 sets of pants, pick one of the 3 pairs of shoes. There's 90 different combinations. Six people can be put into a queue in 720 different ways. Why? Well, whoever is placed first, it can be any of the 6. The person who is picked second is one of the remaining 5. So that's 6 times 5. The next one is any of the remaining 4. That's 6 times 5 times 4, and so forth. So this is in fact what is known as the number of permutations. And it's called the factorial, 6 factorial. I hope this is familiar to you. This is often used in combinatorics, right? So the sample space of, let's say we have 6 people, I say, get in line. They get in line and I look at them, there are 720 different possible outcomes for this way of, in the way of how the people got in line. Question, review questions. Think about this yourself. Don't need to go groups here and don't need to answer here, but think about this yourself. I'll ask this at the end of this course. If I have a deck of cards, there's some kind of game that involves us picking one card at a time. And the next step that we do in this game depends on what the card is. There are 52 different cards. And the game ends when the deck has been played through. All the 52 cards have been picked. How many different games are there? How many different ways there are this game can go? Just as a review question. Think about this. I'll ask it later. In general, okay, repeat the question, okay? We have a game. I don't know what the game is, but there are 52 different moves in the game that can be made. Each move of the game is determined by the next card that we pick from a deck. So we shuffle the deck first, and then we pick one card, we make a move based on what that is. We pick another card, we make a move based on what that is, and so forth. There's no choice involved, it's just picking the card. How many different results of this game, I mean, by result, I mean the whole sequence of the game. How many different games are there? How many? Yes, that is correct. It is 52 factorial. Exactly. It's a huge number, isn't it? You know how big that is. Figure out. It's very big. So we have n elements. I mean, another thing that in combinatorics is often happens. We have n elements and we pick k of them and put them in a particular order. So let's say that I have 46 students and I pick 3 of you at random. One of you is a gold medalist, the other one is a silver medalist, and the third one is a bronze medalist. How many different ways are there to get these results? Well, the first one can be any of the 45, then it's 44, and then it's 43. So it's 45 factorial divided by 42 factorial. Alternatively, it's just, you know, the product there, C here. So let's say that there are 16 teams that are playing in the Ice Hockey World Cup finals. There's 16 factorial different rankings, but we forget about how the others are ranked because we only are looking at the top 3 positions. The number of different results for the top 3 positions is 3,360. By the way, be mindful if you are a betting person. Do not think that, okay, I'm going to bet on Germany winning and you know, I don't know, Switzerland being second and let me think some other, can't think of any. Well, the others are pretty, that I can think of are pretty equal there, but let's say Germany winning, Switzerland being second and Finland being third. That's probably not a good bet, even if it has a very high probability. It's not very likely to happen, right? So it doesn't mean they're equally probable in real life, right? So look at these examples. You can do it at home. I just want to get to the part which, here's an important thing. It's called the K combination. The K combination is that we have n elements and we pick any K of them. They don't have to appear in any particular order. So for instance, I'm going to pick 5 of you to form a specific group. It doesn't matter in which order I pick the 5. I pick 5 out of 45. So that would be called 45 choose 5. So n choose K. These are called the K combinations from a set of n. The lottery works like this. You pick 7 numbers out of, I think it's 40 numbers and so forth. This should be something familiar. It's fairly easy to calculate. I'm not going to spend time on this combinatorics. That's not a very big issue in this course. There's going to be some discussion here and in the exercises, but this is not core material in the sense. I just want you to learn this a little bit because you're going to be needing this somewhere else. All right. It's very easy. If you think about it, if we have K combinations, you know, the number of ways we pick these K persons from n or K elements from n, let's say that that's X. So each of these K combinations has a K factorial different permutations. And we already know that that we get by n factorial divided by n minus K factorial. And we solve for X, we get the formula of n choose K. This is also related to the Pascal triangle. You can Google it and look at that. I'll put some exercises on that we'll talk about. So you see, during the lectures, I often go through these calculation-wise examples pretty rapidly. The reason is we'll discuss these more in the exercises and we'll do some exercises and we'll learn them there. I would like you, I mean, I'm not going to spend a lot of time during these lecture sessions on doing these computations. I'm going to explain the brief outline of how it works, but yeah, we'll use the exercise sessions on this. All right. Here's an example, some examples. I'm going to stop at this point here. So this is the last thing that I'm going to discuss. So one of the places where combinatorics occurs is when we do things like cryptography. Again, this is not really cryptography here, but I mean, you know, your idea is that if we have 26 letters and 6 are vowels and 20 are consonants, let's say letters from A to Z, we got 26 to the power of 5 different 5-letter strings. So if we're encoding something, this is how many 5-letter encodings we have. The reason why your password needs to contain special characters and numbers is to increase that number from 26 to something else. The number of strings where the first letter is a consonant and the second is a vowel, third is a consonant, and fourth is the same vowel as the one before. The last is any vowel. You know, the first one is any of the 20. The second one is any of the 6. Then it's 20, and then it's 1 because it must be the same. So that's 14,400 5 letters words that have these characteristics. The number of 25 letter strings where a single letter may appear only once is the number of 5 permutations. So the first one is any of 26, second one any of 25, and so forth. Now here are some review questions for you. Do you know what an anagram is? Who doesn't know? So an anagram is a word that has exactly the same letters. So if we have some word, and how many anagrams does it have? A 5-letter word. Does it depend on what? Yes, that is true. Okay, so one suggestion is 5 factorial. That is true if what?
If no letters are the same.
If it has the same letter more than once, then the relative order, let's say if it has 2 A's in it, then the relative order of these 2 A's doesn't matter. So it's actually that diminishes the number of anagrams because the same letter, if the same letter appears multiple times, then well, a trivial example, if it's a 5-letter word, that is simply ah. Okay, so this a. Let's say I'm going to type it into chat a. So it has no other anagrams because it's so it depends. This is a trick question really. The number of anagrams of a given word depends on the letters they're in. But if all the letters are different, then it's 5 factorial minus 1, of course, with the origin. But let's say we agree that every word has 1 anagram itself. So 5 factorial. The number of 5-letter sets of 5 letters. How many are there? Well, there's 26 letters. No, not exactly. No. It's this. Let me just go there. It's actually this. 26, choose 5. Isn't it? There's 26 different letters. You choose 5 of them. So there are 26, choose 5. Check that number out. That's a relatively large number. Not an astronomically large, but relatively large number. And the last one, we will discuss this in the next lecture. How do we get this? The number of 5-letter sets with 2 vowels and 3 consonants. So how many ways of picking 5 letters are there so that you get 2 vowels and 3 consonants? So this is going to be a puzzle for the next time. We will discuss this in the next session, I think, or the following one. This results in what is called the hypergeometric distribution, and we'll talk about that later, but it's not yet an issue here. So this is just a warm-up of these concepts of probabilities. I'm giving you homework now, or things to ponder at home, is to figure out these things. The product rule, remember how that works. Remember the concept of permutations. The concept of K permutations, you just pick some number and permute them. The number of K combinations. Those are the things that I want you guys to memorize and then, reflect on maybe this example. Next time we'll talk about the axioms of probability calculus. We come up with a mathematical model of probability calculus. I'm going to end the recording now so we have time for some questions.